I've started the recording, and David, we look forward to your seminar.
Okay, thank you. Good morning. So today I'll be talking about the structures of lanthanide-ligand complexes with, how we resolve them with molecular dynamic simulations and with EXAFS. And go. So I'll first talk about a little bit about the lanthanides and why we care about their structures in solution, and then about the simulation methods we use and some initial results with the lanthanide aqua ions. Then we'll have a break and I'll talk about lanthanide-ligand complexes in different protonation states in aqueous solution. Then another break and the lanthanide-ligand complexes in non-aqueous solutions. So the lanthanides are key components in many technologies we use, such as medical contrast agents. They're also present in petroleum refining catalysts. They're found in the motors of electrical vehicles. They're they form also permanent magnets, so they're found in many electronic applications, such as smartphones, guidance systems, wind turbines. And their properties, we mostly care about exactly what is their structure, and because their properties depend on that structure. So for example, a very well-known case is gadolinium DTPA. It's a MRI contrast agent. You need the ligand DTPA to bind the gadolinium strongly so that the gadolinium ion does not become unbound. You need the ligand to be water soluble, and then also you need at least one water molecule to be coordinated for it to have for the MRI contrast. So the lanthanides, when they're in solution, they're mostly in their 3+ oxidation state as ions, and they want to stay like that. So they all have a very similar chemistry, but they have small differences in their ionic size due to contraction across the series. They form coordination bonds that are mostly ionic. And the lanthanides plus scandium and yttrium are the rare earth elements. And perhaps you've heard that the rare earth elements are critical materials, and their supply chains might be at risk. But they are, in fact, abundant, but they are just very difficult to purify. They're more common than platinum group elements like gold. And the most abundant ones are lanthanum and cerium, and there are some that are actually really rare, like lutetium. And rare earth-bearing ores, they typically have many lanthanides together. So one of the most desired ones is neodymium for the magnets, but you find small amounts of neodymium in ores that have large amounts of lanthanum and cerium. And that's a picture of the Mountain Pass mine that's in California, very close to Nevada, like to Las Vegas. And there they are, again, it's operating, and they are mining rare earths, and they get bastnasite, and it's mostly has cerium, but as well as many other rare earths. So from the mining process, the mining process is many steps, and it's very complicated. You need to separate the rare earth bearing ores from the non-rare earth bearing ones, and eventually you reach a solution that has multiple lanthanide ions. And you never find them on their own because, well, naturally occurring ores, you have many of them present, and if you recycle electronics, there are usually, again, more than one lanthanide. And then to separate lanthanides from each other, solvent extraction is used. And this solvent extraction step, which is very unsustainable because it uses large amounts of solvent and energy. And that is because of their chemical similarity. The selectivity of the ligands is very poor. So I'm going to make a simplified example just to illustrate how the effect of ligand selectivity on the lanthanide. So you have this ideal feed that only has 2 elements in water, and then you have an organic solvent, and then with the solvent you have a ligand or an extractant, and that ligand is going to bind the lanthanide and then bring it to the organic phase. Now, I am not showing the binding equilibrium because it's not exactly clear where it happens. If it happens in the interface, if it happens in the aqueous phase, there's still a lot to study there. But how much lanthanide ion is transferred is going to depend on the binding and on the relative solubility, and then you bring to the extract the lanthanides with the ligand. And how much of one lanthanide is extracted compared to the other depends on the selectivity of the ligand that can be described by the separation factor. So if a lot more neodymium comes over, it's because that ligand binds neodymium more strongly than cerium. And then the separation factor describes, the separation factor is the ratio of the equilibrium distributions of how much ends up in the extract and how much is in the raffinate. And solvent extraction is typically done in multiple stages. Here's the feed that includes the free lanthanide ions, and it's placed in contact with the solvent. And with the extraction factor that depends on the equilibrium distribution and the solvent to feed ratio, so how much solvent you add compared to the feed, we can estimate, here I did some quick calculations of how much solvent to feed ratio you need to separate the neodymium from the cerium. Using these two are extractants that are used industrially. And so their separation factor between neodymium and cerium is small, so it will only bind neodymium a little bit more stronger than cerium. And so you need very high solvent to feed ratios in order to separate them. And that is why the solvent extraction is so unsustainable. However, if we would have extractants or ligands that are a little bit more selective, it improves the process feasibility significantly. So that is the motivation as to why we care about the solution structures. The separation factor is going to depend on how the lanthanides bind with ligands in solution. And so that is our research motivation. We want to predict the structures of lanthanide-ligand complexes in solution, mostly using molecular simulation techniques. And then from the structures, properties can be calculated, for example, separation factors or stability constants. And although we're mostly interested in the applications around the solvent extraction and separation, there are other projects that also we're involved in collaboration with chemistry here at UNR. They're very interested in the spin properties of lanthanide-ligand complexes in the context of like single molecule magnets. But again, it's the structure that defines the properties, and so we're very interested in determining the structures in solution with simulation. And then we use EXAFS to verify the structures, and so EXAFS is great to differentiate local structures in solution, and so we use it to resolve the coordination structure around the lanthanide ion. So the challenges with resolving lanthanide-ligand complexes in solution is that the lanthanide ions as 3+, they are reactive, and you have very large coordination spheres that are dynamic. The ligands are flexible and can change their conformation, and also you have a competition of binding sites between the ligand and an ion and solvent molecules. And then unlike crystals or solids in solution, there's a lot more degrees of freedom. So it's a lot harder to resolve their structures computationally or experimentally. And so computationally, we need an approach that is going to combine both chemical reaction to make and break the coordination bonds and molecular sampling due to the dynamic nature of the coordination sphere. And so we use molecular density functional theory-based molecular dynamics. We set up periodic boundary conditions with explicit solvent molecules to simulate the solution phase. We mostly use CP2K And a couple of years ago, we optimized the pseudopotentials that include all the core electrons and the basis sets that include all the valence electrons. We optimized them to work with the PBE functional in CP2K that has a mixed Gaussian and plane wave approach. So we did put the F electrons uncontracted in the basis set. And then there's the additional plane waves for the long-range electrostatics. We solvate with explicit solvent molecules. We add the counterions to neutralize the charge. And then we do a protocol, a high temperature MD that's just in the simulation more efficient way to sample, and then followed by a simulated annealing. This is just to explore a larger area of conformational space. And then once we have a structure, if needed, we do a production dynamics for further analysis. So for example, from that production analysis, from that production AIMD, we can generate radial distribution functions. So we started with the lanthanide aqua ions because they are really well known. And so we wanted to test if the pseudopotentials and basis sets work with coordination structures. And so our lanthanide oxygen distances are very close to those determined experimentally, and they are better for the earlier lanthanides than for the later ones. I think mostly because in the later lanthanides, the optimizing the pseudopotentials is a lot more challenging, with the F electrons being in the same spatial location as the D electrons. And then we compared the first coordination sphere to ideal 9-coordinate and 8-coordinate geometries and calculated the RMSDs. And we found that they don't stay, they don't have one geometry that they're always in, but they are kind of like, it's highly fluxional, and they the geometry changes between different ideal geometries. And then, so also to compare to experiments, then we predict EXAFS, and we use FEF to generate the spectra from the simulation. So here, if we take one simulation frame, we would generate like one spectrum. But we need sampling, because in experiments, you do a measurement, and that is of many, many structures, right? That's like 10 to the 23 molecules in there. And so experiment is bulk, but MD generates atomic conformations that are just one frame. And so we need to sample from the simulation in order to generate a sample that is representative of the bulk. And so we perform the FEF, the generation of the Chi-K spectra. We found 200 times is a good number. If we, like, for example, if we move up from 50 to 100, the spectra changes a lot. If we move to 100 to 150, it still changes. And then around 200 is when it stops changing. So we generate the production AIMD, and then we predict EXAFS spectra for many frames, and then we average the spectra. And then that is the spectra that we compare with the measured ones. And so this is a direct unfitted comparison. So we're just overlaying the spectra predicted from simulation, that is from many frames of simulation, and the spectra that was measured by experiment. And in the case of the lanthanide aqua ions, we found a very nice agreement with neodymium, and I think also a very good one with the later lanthanides. And you see the difference here because we're not fitting it, we're just directly overlaying. So this in some ways tells us how far our simulation is from experiment. And our simulation is closer to experiment for the earlier lanthanides than for the later ones. So we use Athena to process the experimental data and also to upload the Chi-K from FEF and compare them. And so if it's not a good match, we redo the simulation to try to identify the molecular conformations that are representative of experiments. So that is why we're not fitting, because we want to see what simulations are representative of experiment. And so I think now is a good time to pause for questions, and then I'll start to talking about the Lanthanide-Ligand complexes in aqueous solution.
Thank you. It's a great start. I really appreciated the introduction. We have a question from Matthew Marcus to start.
Yeah, hi. I was wondering, you said that the simulation was done, or that the final simulation was done at 0K. And so I was wondering how you got the radial distribution right in the absence of thermal motion, or was the final production run done at a higher temperature?
Yeah, no. The production MD can be done at any temperature, but so this first part of the protocol is kind of like to find one optimized frame to start with. So
okay.
Yeah, so it's hard to know beforehand like exactly what is going to be the arrangement of the molecules. So we do the high temperature MD and the annealing to 0K to find a good starting frame. And then the production MD, it can be set to any temperature, room temperature, whatever temperature. And of course, there's going to be also, we run it until we get 10 picoseconds of equilibrated trajectory, but depending on the temperature, the first 1 or 2 picoseconds might not be equilibrated, but we use then only the equilibrated part for analysis.
Okay, thanks.
All right, Anatoly, you have a question?
Yes, I have a couple of questions. So first, when you go back to that equation you used to construct theoretical EXAFS, you had sigma square and coordination number. Is it a mistake, or you really used them in your in your MD-EXAFS construction?
So this is what we use like FEF. We just use the code FEF.
I know, but you wrote here sigma square and you wrote coordination number. You did not use them as obtained from MD, did you?
No, we just use the coordinates from MD.
So what's the meaning of this equation?
The meaning, I mean, that is just the chi-k, the EXAFS equation.
But that equation is obtained in the approximation that your unknown GFR is Gaussian or nearly Gaussian, which is not the case here. So how can this equation be useful?
Yeah, maybe that's not a good idea to put that equation there.
I think you used pair. I think you used pair contributions or multiple. I mean, all contributions kind of obtained for a snapshot as your simulation obtains, right? That you did not have to include any sigma square or coordination number because you could use the atom by atom calculations. Is that what you did?
Yes, that's right.
And how many atoms, how many lanthanum atoms were in the simulation box? Maybe you said that.
One lanthanide. We use one lanthanide ion, and this is the lanthanide, and those three are like the counterion, the chlorides, to neutralize the charge.
Thank you. And I have two more questions. Try to be quick. So first is, you mentioned that there is fluxionality in the time domain.
Yes.
What is the typical time of, for example, changing the configuration from, let's say, octahedral to, I don't know, pentacoordinated or anything like that, compared to 10 picosecond trajectory time?
So in the 10 picosecond time frame, we don't see changes in coordination number, but we see changes in the geometry. So it might change more than we will have more than 1 or 2 changes between, like, for example, the cap square antiprism or the trigonal prism. So it will sample the change between these two. But if you have, for example, one of the middle lanthanides that fluctuates between a coordination number of 8 and 9, the ab initio MD will not sample the changing coordination number from 8 to 9. So there will not be water exchange events.
Okay, I don't want to hold too much, but one last question. E0 and S0 square, how did you handle that? Because when you compare raw data, they depend on the choice of A0 in the edge, right? So
Yeah,
how did you match that?
So when you put in Athena, the E0, you cannot change it for the chi-K data that you upload, the theoretical one. So we only change, so we have to change it for the experimental one to match the theoretical one. So
Okay.
I mean, I know that the one of experiment is the correct one and should not be changed, but in some cases we did not need to change E0 at all. It will just it looks fine like that. What we want to change E0 is to get the best matches possible in here, but then because we cannot switch it for the theory one, we just switch it for the experiment.
All right, thanks.
Yep.
How large are the shifts typically following up?
Very small shifts, and sometimes we don't even need to shift them.
Perfect. Thank you. You should continue. That was great.
Thank you. Okay. So we started working with lanthanides with EDTA and gadolinium DTPA. And these ligands have many protonation states. And in water, they're gonna be either protonated or unprotonated. And so if you start from the completely unprotonated state, and that's going to be in very basic conditions, as you become more acidic, the sites that first become protonated are like the amine sites, and it forms like pseudoionic species, kind of like amino acids, and then the carboxylates become protonated. And we started with europium EDTA a couple years ago as the first ligand after doing the aqua ions, because it was a structure that is known from crystallography and from EXAFS. And so we were able to replicate the structure. So the simulation box has explicit solvent molecules, but then here I'm only focusing on the coordination structure. And so the ion, the two amines are going to buckle to coordinate with the ion, and the carboxylates have a monodentate coordination and 3 water molecules. And our lanthanide oxygen and lanthanide nitrogen distances are about 0.05 angstroms from those determined experimentally. And then so we moved to different lanthanides with EDTA. We also simulated lanthanum and gadolinium and lutetium. And we see that as you go down the series, the lanthanide oxygen nitrogen distances, they become shorter. So there's some contraction there. And then we simulated the system with different protonation states. So at pH 11, EDTA is EDTA 4- completely unprotonated, and at pH 7, EDTA is EDTA with 1 proton. I just have to be very clear here and clarify that at pH 7, the complex is in this form, completely unprotonated. But what we mean here is that we are simulating the complex in a ligand, in the ligand protonation state that corresponds to pH 7, but it's just it's not the same the complex, because the pK values of the ligand are not the same as the pK values of the complex. And so if we add a proton here, if this site becomes protonated, this lanthanide nitrogen coordination bond is broken, and you have more water molecules come in. So here we have 4 coordinated water molecules, and there we have only 3 coordinated water molecules. And so for time, I didn't want to go in too much into the electronic structure calculations, but then from the structures that we identified in simulation, we used all electronic structure calculations with relativistic effects to calculate the binding energies. And then another reason we picked EDTA is because the stability constants are known from experiment. And from the stability constants, we can get free energies of binding. And then the magnitudes of the free energies of binding are going to be very different from the magnitudes of the binding energies from computation, so we can compare the ratios. And the ratio of the binding energy, it essentially is the separation factor. And so we are replicating the trends from experiments, and for this talk, the main message is that in order to predict the properties, you need to know the structure. And so in order to get the right trend with the protonated EDTA, we need to have broken this coordination bond and added another water molecule. And in order to get the trend down to lutetium, it's only 2 coordinated water molecules instead of 3. And so we also are studying gadolinium DTPA, that's the contrast agent, and if the dissociation of gadolinium can happen if the DTPA ligand becomes protonated, and then the gadolinium dissociates. Another motivation as to why study these ligands in different protonation states is that in solvent extraction, to recycle the extractant or the ligand, acid is used to strip out the ion. So if you want to unbind the lanthanide from the ligand, you add acid. And so this here is not predicted EXAFS, this is measured EXAFS, and we find different coordination structures if between the free aqua ion and the gadolinium DTPA at pH 1 and the gadolinium DTPA at pH 11. So we see changes in the coordination structure between when adding the ligand and when changing the acidity. And so we wanted to now look at this complex, and that we have now the experimental EXAFS and compare it. So the experiment would be this. We measured it, and then in MD, especially if you're doing ab initio MD, your starting conformation is going to bias what conformations you're going to like explore in the simulation, what you're going to sample. And so you have to make some assumptions in what the first coordination and second coordination sphere looks like. And then we run the simulation and get a sample of solution structures. And then we use FEF to predict the spectra and directly compare them. And so here the measured spectra is kind of like our standard that we want to replicate. And if there's no agreement, that it means we made the wrong structural assumptions, or maybe our simulation isn't sampling properly. And so we return to the simulation and see if we get a simulation that is representative of experiments, and then let's see if that predicted spectra is going to be a better match. And so we started with the unprotonated gadolinium DTPA, and we performed the ab initio MD simulation for 2 purposes. One is, well, to compare, to generate the EXAFS and compare with experiment, but also to tune classical force field parameters for classical MD, because it allows for longer simulation times and length scales. And classical MD will allow us to sample events like in the aqua ions, the change in coordination number, or solvent exchange events that we can't get with ab initio MD. And so this frame here is the classical one. We used a smaller solvent box with ab initio MD. And so because DTPA has so many protonation states and there were so many complexes to simulate, we wanted to move to classical in order to simulate all of them. But then what we see is that there is a better agreement with ab initio MD than with classical. Here you see, I guess, this difference here. It's about 0.1 angstroms, and that is as close as we could get. That we use the OPLS force field. Maybe we need a different functional form to get a better agreement. But we get better agreement with ab initio MD because I guess we're mostly interested in the first coordination sphere, and the pseudopotentials and basis sets are better at predicting the lanthanide oxygen and nitrogen distances than the classical MD. But still, the classical MD gives an acceptable agreement to determine what is the molecular arrangement or the molecular conformation around the lanthanide. And so comparing MD-EXAFS with EXAFS also allows us to test alternative conformation. So I had mentioned that the protonation states here if you go from basic to acid, first amines, and then carboxylates like a Switter ion, and then we were just wondering, well, what if we just tested this neutral compound that has no Switter ionic behavior, is uncharged. We complexed that with gadolinium. We ran the simulation. We saw the protons come off and form H3Os in the solution, and then we predicted the spectra, and we just don't see a very good agreement at all. And so comparing MD-EXAFS with EXAFS, it's of course very nice when you get a very good match and you say that is the structure from experiment, but it's also a tool to tell us, like, no, this conformation is very unlikely to happen. Though the simulation is definitely not representative of what's being measured experimentally. And so here we did classical simulations of all of these complexes. I am only showing the first coordination sphere, but this is in full solvent. And we see that as the first proton comes in here, it just because of the shape of the ligand, breaking this coordination bond makes this coordination bonds, and those with the carboxylates like shorter, and so there's no space for the water anymore. But then as the second amine becomes protonated, you're breaking ligand coordination bonds and replacing them with solvent coordination bonds. And this keeps happening as the functional groups become protonated. You break coordination bonds with the ion and you replace them with water. And by the time that you have only one unprotonated carboxylate, it's just binding monodentate. This molecule here is triplet. We use triplet anions because those were the ones that were used in the measured EXAFS. And so from the classical MD, not the ab initio MD, but from the classical MD of this species, we generated the spectrum and compared it to experiment. And the agreement with experiment is not as good as for the unprotonated case. And so we have the ligand isn't binding as tightly and it's occupying less coordination sites. And so we have a more dynamic, less structured coordination sphere. And so it's harder in the simulation to get those samples that are representative, those conformations that are going to be representative of experiment. And so in there, I can pause before I move to the non-aqueous systems.
All right, thank you. We have a question from Fernando Villa.
Hi. I was just wondering, I mean, it seems like your K range in the experimental EXAFS is pretty decent, and there isn't that much noise. You could actually try a traditional EXAFS fit just to see what type of parameters, structural parameters you get, and then that would actually guide you in your selection of possible structures from the MD.
Yeah. I guess the fitting procedure is I guess I understand MD a lot better than the fitting procedure. It's something that I'm I guess still learning, but yes, you can I think, yeah, the fitting procedure can tell you, it can give you good ideas of what is the proper starting conformation with MD. I think, thank you for that recommendation.
Yeah, you should probably reach out. There are tons of people that would actually be willing to do the fits for you. just to have a pretty decent idea. They work. I mean, we have done studies of this type of things, and the fits work pretty well. Like Matthew. I mean, probably Matthew is gonna, and you is gonna follow up. But I mean, they look sufficiently clean. Those first shells are sufficiently clean that you would actually be able to fit them.
Yes.
Thanks, Jerry.
Thank you, Fair. Matt Newell, you have a follow-up?
Yeah, I do. So this is just exactly a follow-up to Fair's question or point. Right, so if you could do those fits, they look, the RDFs you showed look pretty peak-like, maybe slightly skewed, but fairly peak-like. And then from that, you would get fitted RDFs, and then you could use that directly with the structures, the MD structures. You wouldn't need to do the FEF simulation from all of those, from 200 structures. You could just analyze what is the RDF and what is the RDF that the EXAFS imply. And yeah, I get that doing the MD simulation in the end is very helpful, but that might guide you and be a little faster.
Yeah, thank you.
And then we have a follow-up from Anatoly.
Just very quick comment to Fernando's question, and also to the comparison with possible fits. It's important because this method proves very powerful if the distribution that you obtain is very anharmonic, asymmetric, and cannot be probed by using any kind of cumulants, because this series may not converge too fast. So we showed, and probably not just us, but maybe others, that in molten salts, metal ions in a molten state show very strong anharmonicity, precisely because of this fluxional nature of the environment, coexistence of different complexes with different distances, and their GFR is unique and cannot be approximated by cumulants well enough so that fit results will give very strong underestimation of coordination numbers. So that's something may even enhance or emphasize the importance of your method, but I think it's important to compare. So I'm just in favor of that.
And now we have a very brief rebuttal from Fair.
No, it's not a rebuttal. It's just a comment. I just wanted to point out that in this particular case, in my experience, the asymmetry in the oxygen first shell is not coming from actual dynamics, but it's actually coming from asymmetry, static asymmetry in the distances of the oxygens. There are like 6 of them or something like that, or 8 of them, I can't remember. And they all have slightly different distances, and that actually makes the asymmetry. So it's pretty much non-dynamic. It's fairly static. So I just wanted to.
With that, we'll let David continue.
Okay, thank you. So we're also studying this system, europium with terpieno2 in acetonitrile. And this is the collaboration with, this is not in the context of solvent extraction, but this is Sergey Barganov is my collaborator in chemistry at UNR, and he's very interested in spin properties. He's more an electronic structure research group that they go and they are very interested in how the spin properties will vary between like solution or crystal phases. And so with our collaboration is with the MD, we can see how the solution and crystal phases change, and then we work with them to go into the spin properties. But I'm not going to talk too much about spin properties, but about structures and how we use EXAFS to verify them. And so we studied europium terpieno2 with nitrate or triplet. Solution structures were unknown previously, and from X-ray crystallography, our collaborator Ana Betancourt-Diaz crystallized this this complex, and you show a 10-coordinate system with the nitrates as well as the terpieno2. And so we wanted first to see how much does acetonitrile solvation changes the crystal structure, and not so much when you have nitrates. Yes, the angle of like the conformation of the ligand is going to vary a little bit. It's not going to be in the exact same angle, but we still see the same molecular arrangement. We have the ligand binding, and the 3 nitrates are bidentate. And so, and then here we got some very nice agreement with experiment. The EXAFS, the spectra, they're a very good match. And then when we, again, what I was saying, that you can run simulations of anything, and then predicting the spectra is just this great way to see how well does it match with what's happening in experiment. And so our simulation, when we ran the ab initio MD, we did not see an anion solvent exchange event. Those nitrates always stay there, but we just started a simulation with a different conformation. Let's just put the acetonitriles in there and move a nitrate out and predict the spectra. And we see a much better agreement with only nitrates. So the simulation that only shows the nitrates, we think, is more representative of what's happening in solution. And when we change the counterion from nitrates into triplets, the triplets will bind monodentate instead of bidentate. And so that loss of coordination sites, they need to be replaced by something, and it's replaced by acetonitrile coordination. And so when we change the counterion, we see that it's not only the counterion that's different, but you change the entire coordination sphere, because now this allows solvent molecules to come in. And we also did it with just the nitrate salt with no ligand, and we don't get as good a match in this case. And this is again, when we have a ligand occupying many of the coordination sites, we have less degrees of freedom to sample in the simulation. But when you have such an open, a lot more degrees of freedom, it's hard to find the simulation that's going to generate this representative sample. And so that's the europium salt. The other possibility that we thought when we were writing this paper is that perhaps water, there was a little bit of water contamination in the experimental sample, and if in highly non-aqueous conditions, the water molecules are going to most likely find their way to coordinate the europium. And so the solvent changes the counterion coordination. So we also measure the europium aqua with triplets, and the triplets do not come into the first coordination sphere. However, in acetonitrile, they will coordinate the ion. And so how to improve structure sampling and comparing with experiments? We explored the use of a global optimization algorithm instead of MD to generate the frames and predict the EXAFS. And we're using the Northwest Potential Energy Surface search engine that will explore other regions of conformational space. And what the global optimization algorithm does, it generates many different conformations. Oh, I forgot to put in the energies in there, but it's like everything's within 2 kcals per mole. And then from the generated frames, instead of those generated by MD, we can predict the spectra and compare with experiments. And we see a good agreement with the ligand. The peaks are sharper because there are less frames used. So if we use more frames with MD that are going to really take in all the conformations, not just optimized structures, the peaks are less sharp. And this is kind of like a work in progress, but I still wanted to put it in here. So in blue is the experiment, the measurement of the neodymium nitrate salts, and in red is a spectrum that we just combined it from different molecular arrangements. So we did one simulation that has 6 nitrates, and we used another simulation that has 3 nitrates and 3 acetonitriles, and we're trying to find kind of what's the right mix that's going to find the best agreement. And we still haven't made complete sense of this. It's something that we're still thinking about. It's work in progress. I don't have yet the best explanation, but I still wanted to share it here. But what it suggests is that in experiment, there's going to be different number of nitrates coordinating. It's not going to be a fixed that every single neodymium has the exact same number of nitrates all the time, but in experiment, it's kind of like a dynamic structure in solution. And so we're mostly a simulation group, and EXAFS is just this great way to verify our simulations to see if they're matching experiment. And we're mostly interested in lanthanide-ligand complexes in solution, and this approach allows testing different molecular arrangements. And so the measured EXAFS is kind of like the standard, and we then see if our different simulations, how well they match. And so I like to acknowledge the students and postdocs in my group. So Richard Shirey, a PhD student that graduated in 2002, he did most of the simulation work with the aqua ions, and he's now at PNNL. Ravi O'Brien was a master's student that worked with EDTA and DTPA, and he graduated with a master in his local industry here in the Reno area. Jera is a current graduate student that took up what Ravi was doing, and Thomas Summers is a postdoc in my group that's been working on both the non-aqueous and the aqueous the lanthanide-ligand complexes. And then Thomas spent some time at PNL with Difan and Banda to learn the global optimization algorithm. I want to especially acknowledge John Fulton and Shelley Kelly. So John, he taught me a lot of the FEF and the MD-EXAFS. And by the way, the comments in the previous discussion about comparing our FEF, like FEF-MD results with the fits. I think John did the fits with the aqua ions, and we do compare that with only the aqua ions, but I have not done that with the ligands. Shelley Kelly at Argonne. So in March of 2022, I went to Argonne, and we did all the measurements for the lanthanide-ligand complexes, and she's the beamline scientist that helped me with those measurements. And Mali Balasubramanian worked with John Fulton to get the measurements of the aqua ions. This was several years ago. And my experimental collaborator, Ana de Betancourt-Diaz, she's been a great collaborator, learning a lot about the lanthanides with her, and she's the one that actually synthesized the complexes. I took them to the advanced photon source, but she has the wet chemistry lab. And funding comes from the National Science Foundation and from the U.S. Department of Energy. And I would like to thank you for your attention and your time, and Jerry for the invitation. And I just leave you here with a picture of the UNR campus in Reno, and there's the Sierra Nevadas. So thank you.
Thank you. I really enjoyed the talk. Thank you for the care. We have a few questions for you. We'll start with Matthew Marcus.
Yes, I was wondering. Cerium is unusual in that it has a 4+ oxidation state. So I was wondering if somehow the conditions could be tuned so to make the cerium adopt that state, which would then make it more distinct from the other rare earths, and therefore perhaps easier to separate.
Yeah, so there are I guess cerium is one of the few lanthanides that it can be separated by redox, by a redox approach. They changes to the 4+ oxidation state, and then it can be separated from the other 3+ ones.
Yeah, does that really make a big impact in solving the separation problem? Since cerium is the most common.
I don't know how well the redox approaches scale. So it does work great in like the chemistry lab scale, but then when you go into the industrial scale where it's kilograms and kilograms of feed, I am not sure there what's I think it's still done with solvent extraction. So the Mountain Pass mine, that's the US, is again mining rare earths, but then after all the mining process, they still send they are still sent to China to do the solvent extraction.
Oh boy.
Yeah.
Yeah, maybe electrochemistry could be used somehow.
Yeah, I think that's an active area of research. I don't know the very latest there, but I do know that they have shown redox separations of cerium, but yeah, I don't know what's the latest.
Thank you.
Yep.
Excellent, thank you. I'll ask a question now. So there's of course a growing trend in the EXAFS community to do multimodal studies where some second measurement will help constrain the modeling of the EXAFS. Here, of course, you have this manifold of possible local coordinations that you're simulating and trying to select from and trying to get equilibrium distributions of. And I guess I'm wondering what would be an example of a good auxiliary method to help refine the EXAFS fitting process?
I still don't understand your question.
Suppose you had some other technique you could also use that would tell you, oh, it's 9 coordinated, and that's what you need to focus on. PDF, RIX, HERF-D.
Yeah. So I guess crystallography can point to a good starting point. So like we did with the terpeno2, we knew the crystal structure, and so that is why we started with the structure with no acetonitriles inside.
Does UV-Vis ever help constrain the distribution of coordinations?
You know, I'm not too familiar with
Okay.
UV-Vis, but
the last thing I'll ask as a spectroscopist here is the HERF-D or RIX in the pre-edge. I do wonder if you ran, I don't know if it would be Orca or ocean calculations for a few of your representative coordinations from that very first project, the simple aqueous chloride system. I wonder if the different coordinations of water would give you different pre-edge features that you might be able to see if the lifetime was suppressed through HERF-D.
I've never tried that. I did use the Orca calculations for the binding energies in order to quantify the binding energies, but not to predict the other properties.
Yeah, part of why I ask is valence to core emission has and also the pre-edge features for the 3D transition metals is very good at seeing symmetry changes.
Okay.
And so that's what made me wonder. It looks like Anatoly has a comment he'd like to add on this issue of multimodal. Anatoly?
Yeah, sorry, just to the discussion of UV-Vis. Yes, UV-Vis is very sensitive in some transition metal complexes and actinides in molten state. Not so sure, but actually, yes, in ionic liquids as well. So it's really very good technique because it has fingerprints for unique coordination states, especially if they're mixed. And this method, AIMD, is really good to analyze mixed states. And UV-Vis can be very handy here, as shown in several papers. And regarding Zanes, maybe a question more to Fernando and others who do that. Is it feasible to do MD or AIMD Zanes for the same purpose as AIMD EXAFS to validate the process? Or maybe maybe others can tell. Thank you.
All right. What's the computational load associated with AI MD Zanes or HERF-D? Do we have a theorist here who can pipe in on that?
Do you want me to answer?
Sure, I'd love it if you would. If you can,
Okay.
yes, please.
It's totally feasible. I mean, they are doing probably probably the AIMDs that they are doing are more computationally intensive than any SANES calculation they are going to be doing after on sampling, because you probably don't need to sample too much. Based on my experience with AIMD SANES, it's perfectly doable. It's just a matter of choosing a bunch and just running the calculations with FEF properly. And yeah, if you stick to FEF, if you try to do anything else, it is going to be extremely expensive. But if you do it with FEF, it's feasible.
Well, we're talking about localized pre-edge resonances and whatnot. So,
well, I mean, you're gonna get the overall shape pretty well, and you might see differences. So,
okay, very good.
you were asking about the computational cost, not about how good it's going to be. So, anyway.
I stand corrected. Very good. Well, we're at 10 o'clock, and I think we've had a great talk and a good menu of questions to stimulate discussion. And so with that, I think we should thank David. I'll stop the recording.